RSA Hardware Implementation. I'm just going to start this up straight away, right? And so I hope you know already then how RSA works, right? We've got P and Q. I've just picked two small, more or less trivial numbers just for an example. And we've got E as well, and I hope you know that E has to have GCD condition 1 with phi of n, right? So the inverse has to exist. Okay, so we've computed the inverse here. Let's just go ahead and start the encryption process straight away. So the message is 123 and it's being raised to public key, right? Reduce modulo n, okay? So, okay, let's go ahead and just start that up straight away because it's going to take a bit of time. The square and multiply algorithm is how efficient exponentiation is done, right? So if you wanted to exponentiate in a naive way, right, and you had, let's say, for instance, I don't know, 2 to the 20th, right, and you just keep going like 2 by 2 by 2 20 times, right? That's bad, right? So efficient exponentiation provides you a way to significantly reduce the number of steps you need to take in order to get to your end product, right? And so there's something else though as well. In efficient exponentiation, remember, it's not just exponentiation in the context of RSA. You're reducing modulo n, right? Remember, it's going to be e raised to some exponent, right? Your message rather raised to your exponent e, right? Reduce modulo n. Okay, is this finished? I think so. 37, 64. Okay, yeah. Let's just let it run for a little bit more just so the values can propagate. All right, I think that's fine. But not long enough. So this is our ciphertext here, right? So we'll put this into the register, 64 as the base, and we're going to disconnect this guy here, and we're going to raise it to our private key, right? Because that's how you decrypt in RSA. Okay, and so I can reset the simulation now and start it over again. Oh, and typically, right, in hardware implementations, this setup is only done at manufacture, and the values you get, right, are literally just burnt onto your chip, okay? And so really, the square and multiply portion is the more important part, I think, but I was really happy to implement this portion as well because I had some fun challenges there that I'll share with you in a bit. Okay, so we've got that finished. Now I can go ahead and start up the square and multiply again down here, so reset. Okay, so let's start that up. All right, so where was I? I think I lost my train of thought there somehow. What was I telling you about? I can't even quite recall. But I think what I was trying to say, okay, you do efficient exponentiation by square and multiply, and I hope you know how square and multiply works. If you don't know, here's like a high-level overview. What you do is you take your exponent, you convert it into its binary representation, and you start from the most significant bit, right? And you move to your least significant bit. Okay, and so at every single bit position, what you do is you square the value, and you start your register, your accumulator at 1, right? And say, for instance, we had a whole bunch of trailing zeros, right? You would square a whole bunch of times. 1 squared is just 1, so it's literally, it doesn't matter, right? But the second you hit a 1, right, what you do is you do the squaring, right, but then you multiply by the base, okay? So you square and multiply, really, and that's it, okay? And by the time you reach the least significant bit, you're good to go. Okay, so it seems as though we're almost to the end. I don't trust this done signal yet. The values usually, the values usually need time to propagate. And there we go. We got back our original plaintext, right? So there we go, working implementation. And so this project was extremely involved. It took me about 3 weeks, really. It's quite difficult, one of the more difficult projects that I've attempted in a while. And I was going to do AES and SHA-256 hardware implementation, but then after doing this, I already have all the primitives, I think, to go ahead and implement those. Anyways, I think those are trivial compared to how you would implement something like the inverse, for instance, here in this ALU. So I'm just going to do the FPGA implementation later on, and so my plan, though, hopefully I can get it done maybe sometime around August or so. It's just an FPGA implementation for a 32-bit CPU, and it's going to have custom ALU instructions for cryptographic protocols, right? So your hardware accelerating these cryptographic protocols like straight. There's only so much you can do when you're optimizing from the software level, right? Because you're limited by what your hardware gives you, right? And I'm going to give you like a direct view of what goes on there, because you notice how slow this SAM was, right? And I'll show you why in a bit, why it's so slow. But okay, and also it's slow because the auto take frequency is like, it's very, look at this, right? 2048 kilohertz. Like, what is that, right? Okay, it's really, really slow clock speed. So okay, I mean, in the context of like modern CPUs where you've got like literally like 4 gigahertz, it's like nothing, right? But all right then. So let me start with the full adder and subtractor. I think is just basic, right? I already showed you how to build this in my Introduction to Digital Logic 1 and 2. This is just an extension. So what I showed you, I think, was a 32-bit implementation. This is a 64-bit implementation. I needed 64 bits because I had to do this with for my division circuit, right? I used, what did I use? Restoring division, yeah, for signed division, yeah, it was restoring division. It was so long ago now. It feels like, compared to like the sea of problems I had to deal with, that was like, you know, the start of the journey, I feel. But okay, let me show you what the division looks like. There we go. So this is the division circuit. It works fine. I'm not going to go through an example. I'm going to show you how the inverse works, right? Because the inverse literally uses all of these operations together. Right, let me see. Does it use division though? I don't know. I don't think so. Oh yeah, it does, right? So it uses division, it uses multiplication, it uses addition and subtraction, right? So it uses everything. So the multiplication though, I'll touch on that very briefly. The multiplication is done by something called Booth's algorithm. So this is really, really fast, by the way, right? As opposed to something like if you just use the combinational circuit and you have to wait for the values to propagate and things like that. You get this done in like 32 clock cycles. So it's really, really fast. And then there's obviously optimizations that you can do on this as well. So they can get even faster, and there are things like Wallace trees and so on that you can implement. So you can do much better than this, to be honest. But let's do like a trivial multiplication. It doesn't matter. Let's just go to the inverse, because the inverse is doing multiplication, right? So how did I set up this inverse again? So you take in R0, you take in R1. Is there anything else? No, because so this inverse was done via the extended Euclidean algorithm, right? So this is really a hardware implementation of the extended Euclidean algorithm. And normally that's done in software level, and I think I understand why now, right? Because this thing was a pain to implement, to be honest with you. Quite a pain. So let's do an example though. Let's say, what can I do? I can do like, let's find the inverse of 3 modulo 11, right? So let's find the inverse inside of that finite group. So we'll say 3. Right? Oh, but you need to take the higher number as R0. So we're going to say 11. So this should be 11, 10 and 2 and 1, 11. 8 and 2, 10 and 1, 11. Yeah, that's right. And the 3 here. Okay? Let's kind of just zoom out a bit. And there's supposed to be a reset button somewhere. Here it is. So there we go. So we should be good to go from here. And let's clock, right? Well, it's not clocking. It is. It isn't. I don't know. Oh, it is. Yeah, it's working. It's working. Okay, it's going behind the scenes. So now we just wait for this done signal to come through from up here, right? All right. So right now, what is it doing really is just trying to find like linear combination, right? Some linear combination of vectors that's going to produce. I think that's it. Yeah, because that's really all the extended Euclidean algorithm is doing, right? You have these S and T values, right? And you're looking for some linear combination of the original S and T values. And so here we go, done. And so it says here, so this is the, let me stop the clock. So this here, the value in your T1 register is going to be your inverse, right? And so it says it's 4. Is it 4? So let's think about this. So 3 times 4 is 12 yeah, it's 1, right? So 3 times its inverse is congruent to 1 modulo n, right? Which is 4. 3 times 4 is 12. You reduce that modulo 11, you get 1. So there we go. So that's our inverse. And this had a lot of challenges. I think the first big challenge I had was trying to figure out how to get these registers to update themselves, right? The first instance was fine. The first instance of the Euclidean algorithm was okay. It was the general case that was a pain to implement. And so the way I solved that is I realized that I can actually nest these finite state machines together. And that was like the big aha moment. Like, I was like, oh, yeah. So that makes sense. It gave me the amount of granularity that I needed to sort of control this circuit and get everything to time themselves properly. Because remember, this is not a combinational implementation. This is a sequential implementation. And so timing is like paramount to everything, right? You have to get the timing right. So that was how I was able to sort of do that. And then there's something else too. It's called a one-shot pulse. So the one-shot pulse takes in some one value, right? And then it just sends out like a temporary pulse, basically. And so that was very important. So my circuit is really set up around these one-shot pulses that's listening for done signals all over the place, and so it sort of helps to orchestrate the entire thing. And so there was like a really, really funny case that I spent like 2 days, and this was towards the end of this project as well, right? Where I'm finished with everything, right? And it's still not working. And so I'm troubleshooting, and eventually I realized that somehow an extra bit is being put on the bus somewhere. Somehow or the other, an extra bit is like appearing in the register at initialization, right? And I'm like, well, that's insane, right? That's like black magic. That's not possible, right? Where's that bit coming from? Turns out, right? I had a small connection here, right? That's not supposed to be there. And so what happens is that when this finite state, or this ring counter, if you want to call it that, reaches the end, right? And it came around, it happens so fast, it's virtually invisible. You can't see this happening, right? And it comes through here, and then it immediately jumps across here, and it puts that bit on the bus, right? And it goes into the register. And that was like so insane to me, because I literally had to spend a couple of days like just trying to figure out what was going on there. It was like black magic. It was literally black magic, to be honest with you, because I couldn't figure it out. And eventually, like, I was like, okay, let's just work backwards. And I just worked backwards, and I was like, oh, like hypothesizing like what could go wrong and what could it be. And I was like, you know what, maybe there's a possibility. And I was like, after eliminating everything else, I was like, what if somehow, like, via black magic, right, that we're getting a bit from this line, because it has to come from this particular line. And I was like, oh, wait a second. And turns out that was the issue. And so this particular project here only got more difficult as I moved it towards the end. It did not get easier, right? So let's talk about square and multiply. So this is the regular square and multiply. It's not loading though. Yeah, it's really slow, that's the thing. There we go. Yeah, well, it's a lot of internal error. What did I do? Yeah, I have no idea what I just did. Can I just undo whatever I just did? I don't know. Yeah, let's just undo. Can I just like... Yeah, I don't know why that happened. Maybe I like accidentally clicked on something. So let's just go back to R square and multiply. Can I just reset? Let me just reset the entire simulation. But I don't know why I'm getting an internal error though. That's weird. That is very weird. Let's scroll down and see like what the issue might be. Yeah, that's quite weird. I don't know why I'm getting that error. Let me go back to main. So that's fine. Maybe I need to reset from the main. Yeah, maybe let's try that. And then let's come down to square and multiply. Nope. So maybe, yeah, I don't know why that's the case, to be honest with you. That's strange. And then there's boot reduce mod n. Is the issue coming from here? No. There's Montgomery reduction, which I'm working on. So I wanted to show you, right, the difference between something like Montgomery reduction and how regular square and multiply works reduce mod n, because division is actually a really, really expensive operation. And so I think my PC is just too slow because it's like lagging, crazy lagging. So, and let's try this again. Let's do reset the simulation. What is the internal error though? It's not clear to me at all what that internal error might be. Where's the reset? There's supposed to be a reset button somewhere. There it is. So let me try hitting this reset button. No. Okay, so here's what I'm going to do. I'm going to discard any changes I might have made, because there's a chance that I did something during all that lagginess. And let's open up Baglish project again. Okay, and let's go back to Sam. Okay, good. So apparently, I guess, right? Because I don't know if you remember, but like when I clicked on it, like something dragged in that wasn't supposed to be there. So I think that's what happened. So yeah, it's really computationally intensive, this simulation, right? Okay, and so yeah, let's do square and multiply. But this implementation is reduce modulo n. So this is not what I wanted to show you at all, actually. And so normally though, right, with your typical square and multiply, because I was lazy, I didn't want to do like a separate circuit implementation. But instead of doing like boot reduce modulo n, because this is just your typical multiplication reduce modulo n, you just do you swap out these two circuits here for your typical exponentiation, right? Your typical Boots algorithm, and you would get square and multiply, right? But what makes this so expensive, right, is because after every single exponentiation, you have to reduce modulo n. Because if you don't do that, right, you'll end up with some number, let's say like 10 to the, I don't know, some large number, right? It's basically infinity, right? You can't compute that. And so you have to reduce modulo n every single step of the way. And so every single time you have to do that division, it's very, very expensive. And so there's a better way to do this, though, and it's called Montgomery reduction. And it's so cheap, right? Because, and I didn't do this because I was like, okay, I'm just going to take that and do it in the FPGA implementation. So this is sort of an incomplete version of Montgomery's reduction. But basically what you're doing is you enter into this Montgomery number system, right? And the key to it, though, is you have this radix value, right, which is 2 raised to some power. And what that allows you to do, as long as it's greater than your modulus, what that allows you to do is convert, right, these expensive division operation into simple right shifts, right? That's it. And you see, you do left shift, right shift, and you stay within the Montgomery number system. And so the only 2 expensive portions of this operation would be to, 1, enter the number system, and to leave the number system, right? But everything in between is extremely cheap. And in the context of RSA, we're exponentiating like thousands of times, right? Works out really well. So yeah. But okay, I think that's just about the end of this video. I don't want to keep it too long. Maybe I just tell you like a little bit more about RSA in general. So this implementation, though, is what's called schoolbook RSA. So like regular RSA is not implemented like this at all because of what things like attackers can do, like Oscar, right? Bad guy Oscar can do some pretty bad stuff to schoolbook RSA. And so they actually have like fixed bit patterns at the end and things like that. I don't know how modern RSA is implemented. I'm gonna have to look up exactly, but I do know, like, on a very high level, towards the end, right, you have like a fixed bit pattern and it has to match, right? And so your attacker cannot guess, right? And so you should know one of the implementations of RSA is in digital signatures, right? And so it's basically the same thing. You compute your private key, you send your public key over the channel, right? And then you have your signature. And what you do with your signature is you sign X, right, using your private key, and you send that over, right? So it's basically X raised to your private key, D, right, reduce modulo N, and you send X and you send S over. And then so if you're Alice and you're sending it over, what Bob is going to do, right, is going to check, right? He's going to validate your digital signature, and this is going to provide authentication. It also provides non-repudiation, which I think is also very, very important. And then, okay, this is not all, right? This is like a gross oversimplification. There's like other things as well, like hash functions with digital signatures, but we're talking about RSA for now. And so what happens though, right, is Oscar has S, right? He has X and he has N, and so he can guess some X, right, that's congruent raised to S raised to the E mod N, right? And you can compare against a potentially generate a valid signature, right? And so here's why, that's why you put in the formatting rules into these newer, like patched, patched versions of RSA, right? And so obviously though, anytime you have asymmetric protocols in general, right, asymmetric cryptography you're using, they're vulnerable to man-in-the-middle attacks, right? And so that's where digital certificates come into play, and those are very, very similar to key distribution centers in symmetric cryptography if you were using those. But okay, so I think that's enough from me. So yeah, this was a pretty fun project. I think now I can certainly move on with peace of mind and just go straight back to my more or less hardware implementations, like other things, right? It doesn't have to be like cryptography focused, but like maybe computer architecture focused or more robotics focused kind of projects. But I had a lot of fun, and I certainly learned a lot. So I hope maybe you learned something too as well, right? And obviously later on in the future I can go into more details, like make separate videos on the ALU components, right? So the 32-bit CPU from here I think is going to be trivial. I already have like pretty much everything I need. I'll obviously put in more instructions and so on, but like the most difficult instructions I feel like are already done. and I already have the RAM implementation from my last CPU. I'm going to reuse that. Control unit, okay, that's going to be a bit trivial. I think I can even reuse like some of the control unit from the last one as well. Okay, yeah, and so I'm pretty happy so far with the progress I've made on this one. All right then, well, I hope you guys have a good one.